So hello. We are Demonware. Well, two people from Demonware. And we're here to talk about deploying Cassandra for Call of Duty. So that's me. I'm Tim. I'm a software engineer. That's Seán. He's an operations engineer. And we both work for Demonware. So Demon who? So Demonware is a subsidiary of Activision Blizzard. We're owned by Activision Blizzard. And we write, deploy, and maintain client and server applications for Activision and Blizzard games. We've been around for about 11 years now at this point. We were bought in 2008 by Activision, and or 2007 actually, I think. And yeah, so we've been doing it for a little while. Here's some of the titles that we've been involved in this year. There's also Destiny, which is not there, which released on Tuesday. So we got Advanced Warfare, Diablo, which it turns out was our 100th title. We were involved with 100 titles. There's Call of Duty in China, which is releasing later in this year, and Skylanders, which is releasing in, I guess, next month. We've been involved in a lot of titles. Skylanders, every Call of Duty since Call of Duty 3, loads of Guitar Heroes and DJ Heroes and other heroes and Bond games and, you know, mobile apps, etc. We have a lot of services. We do things like matchmaking, which is, you know, if you want to play a game with someone, you have to say, hey, I want a game, and someone else has to come along and say, hey, I want a game, and then we match you up and off you go. Leaderboards, chat, file storage, you know, leagues, social network integration, you know, uploading things to YouTube, streaming them, big content servers. We have a lot of stuff. We have about 100 services that we use in various configurations for each game. Yeah. So some of the technologies we use. On the client side, we've got C++, of course, because, you know, consoles run C++. They need to run fast. HTTP for web-based applications and websites. And on the server, these are the main things we use. So we're a big Python house. We use Erlang as well, MySQL mostly. We run everything on CentOS, and we use Puppet for automation. There's plenty more, but they're the main things. So we have a bit of an unusual use case. Most people in this industry talk about ramp up. They, you know, you'll start out small. You might have a few customers. You'll gradually maybe gain some popularity, and eventually, you know, maybe you'll have a couple of spikes, and over the years, you'll gradually ramp up and up and up. We have the exact opposite case. So here's one of our games. You can see there's release day. That is the first weekend. That is the peak. This is not working. That is Christmas. And what happens is over the next year or two, these numbers will gradually just tail off. So we have the exact opposite case. We're straight up and then tail off. So this means that, because we're in America, I thought I'd use an American quote. We need to be prepared on day one. We need to know that our infrastructure is going to withstand the load that's coming, and then we gradually consolidate as time goes on for that title. Yeah. So I'm going to hand over to Seán.
So why we chose Cassandra, or why we started moving away from MySQL. We use MySQL for 11 years, 10, 11 years. We're very confident in it. We know what we're doing with it, and we're happy with our MySQL setup. So it needs something pretty big to make us want to switch away. So the big thing that we needed was we needed to share data across DC. And MySQL isn't great at that, especially when you need to master both DCs. You're going to be writing the same data set in both DCs. So that was our big push to move to something different. So we identified about approximately 4 services which we decided to look into and see which of these is suitable, if any. So the first service was our progress store. This is a storage system which is high write volume and a low read volume. Typically, users come online, they read from the progress store, then they write continuously when playing through the game, and that's it. They don't read again until they log off and log back on again. The file size is roughly 4 kilobytes, and it's persistent. So it's your save file, it's your loadout, your weapons, your level of your character, all of that. So you can't lose that. The next one was presence. So presence is a pretty standard service. It's high write and high read. It's constantly pinging, saying, I'm online. Your friends every so often check who's online. So it's transient data. It's very small data size. And the last one, the next one we looked at was messaging. So messaging is mail slash messaging. So it's sending mails or messages to other users. So it's low read, low write. It doesn't happen too often in game. It's like in-game invites for join my party, that kind of thing. And again, transient. We also looked at a fourth service, but about 2 or 3 weeks in, we decided it was too relational and to keep it in MySQL. That ended up having kind of the two MySQL DBs, both DCs, doing cross-hair application. It works, but it's not pleasant to maintain or administer. So the requirements. I mentioned the cross DC. That was our main push. So whatever we chose had to do that, and it had to be master in both DCs and writes to both. The next was consolidation and expansion. As Tim mentioned earlier, we have to build high early on, and we consolidate months or a year later, and we reduce our server size because as the user count kind of drops off. So we typically may spend 3-ish months a year maybe doing consolidations. Maybe a bit less, maybe a bit more, depending on the year. It's a lot of ops time. We have to get people capacity planning involved. We have to get operations involved, development involved, do a lot of planning, and then actually we'll do the work itself. And it's MySQL, it's sharded MySQL, which we do. It's fairly intensive work-wise. And also then you're actually waiting for it to happen, waiting for it to finish consolidation as well, which can take a fair bit of time. The way we typically do it is we silo by title. So we have a single cluster, and that single cluster does a single title. If we're doing another title, we build a new cluster up, and the new cluster does this new title. We keep things very separated because we never want to have a situation where one title will impact another title. Again, this doesn't help with the whole you have many MySQL hosts, and consolidation then becomes a bigger task as well. So another requirement was whatever we picked, consolidation and expansion had to be easy. Manageability. So we had an operations team of about 15 people, 15, 20 people. Because of that, and they're all used to MySQL. So if we're going to rip up MySQL for some of our core services, so the progress stores especially is a required service. If that's down, the game doesn't work. You don't get on. So if we're going to replace one of our core services with an alternative, we need to make sure the alternative was easy manageable, and it was we could script, automate, and make sure that any new people can just read a 1-page or 2-page doc and do the basics, or if they're rang at 2 in the morning with on call, they can actually fix it. Lastly, of course, throughput. We looked at the throughput for each of the services we're looking at from the application point of view. And the throughput for the title we're actually trying to build for was about 1.5 million requests a minute for storage, which is the presence store, about 250,000 for the presence, and about 850,000 recs a minute for messaging. Now, each of these requests, as I mentioned, is from the application level. So if you convert this to NoSQL, non-relational databases, you may be turning that into 2 to 5 different requests. So one of our operations engineers was getting to deal with the whole cap theorem, and as this proves, he had the AP sorted, but not too much the C bit. We shortlisted suitable options. Rake and Cassandra came up the top of the list. They were both level DB. They were both based on DynamoDB. They both would roughly the type of data. Looking into available options, they came close to what we want. They're both easy expansion, both vnodes. We deployed in Cassandra 1.2, and vnodes was a major reason for that. We also rewrote our application backend twice. So we believe in testing our stack. We don't want to use some automated testing tool, which we put numbers in and see how that performs with Cassandra. We want our complete stack built out and see how that actually performs. So we built our stack to use Cassandra and Rake in the back end, and then we did load testing for approximately 6 to 8 weeks of each as an evaluation before actually doing proper full-on load testing. We did find that doing an evaluation of one and then the other made the evaluation of the second one easier. We learned the second one easier because they had many common aspects. Load testing. So the way we did load testing, because multi-DC was one of our main objectives for this, we built 2 clusters. In one DC, we built a cluster with a single CPU, SSDs, and average memory. I think average memory is about 24 or 36 gigs. In the second DC, we had dual CPU, so I think it's about 24 cores altogether, perhaps. We used spindles and high memory, so high memory being about, I think it was 64 to 96 gigs. The reason we did this two very different clusters was so we could identify bottlenecks. So if we had 2 the same cluster, you see there's a bottleneck in I/O or a bottleneck in memory, there's very little you can do other than ship new hardware in or try and upgrade your hardware, which is a pain. So by this, we actually saw, okay, CPU is fine here, but memory is not so good here, and we could actually tweak it then. We could get a rough idea what we were looking at. We use realistic workloads, which is very important. So we can look at our development environment. We can see what the game studios are, what kind of calls they're making, the frequency of the calls in development. Based on that and previous titles, we can make a pretty good guesstimate of what they're going to look like in production. So we use that for load testing, and we load tested using, again, I said, the full spec, the full system. We included peaks and troughs during our load testing. So we typically may just kind of bring up 1 million or 2 or 3, 5 million users and keep with that. With this time, we decided to actually simulate logins and logoffs, and that helped us. Tim will go into later. We also ran a soak test. I think this, from the very start, we decided a soak test is one of the most important things we have to do, where typically our load tests of approximately 3 to 4 hours, maybe 5 or 6. Because Cassandra will change over time a lot, we decided we needed at the very least 3 to 4 days, ideally 2 weeks. I think we ended up with 5 days, because as you always run out of time with these things. Some interesting numbers. So some of the numbers we load tested were, we load tested with 5 million users. At that, it was about 6,000 reads. This is a per node thing. It's about 6,000 reads for Cassandra node, and about 15,000 writes. And at that, it was about 2.5 millisecond read latency at the 98th percentile.
So, as we said, we load tested React and Cassandra. And the winner was React. No, it wasn't React. We thought React would be a slam dunk because, well, it's Erlang based, and we know Erlang. The tooling is actually excellent for React. It performed very well. We did the React testing first, and so we thought, okay, this is looking pretty good. Oh yeah, and we had previously evaluated it as well. One of our engineers had gone into evaluating it for another product previously. So, however, Cassandra was actually the winner in the end. Otherwise, we wouldn't be here. Why is this not working? So the write performance, seriously beat React. It was about 4 times better, just for our workload, that is. It had a richer feature set, it had compound keys, it's got the partition keys and the clustering columns, and that enabled us to do a bit more. React is quite simple, really. It's just key value, mostly, or at least at that time it was. So from a developer perspective and feature perspective, it was much more inviting. Cassandra was much more inviting at that time. The maturity of the code base was it was a bit more mature. There was a bit more community around it. It seemed like it had gone through gone through the wars a little bit and was a bit better off for it. Why is this not working? I might have to use yours.
About the same.
So we continued testing 24/7 until launch. Oh yeah, the other thing I meant to mention there is, so generally speaking, if you mention Java to our engineers, because we're not Java heads, we run a mile. But one thing about Cassandra is that it doesn't really reveal too much the technology on which it's built, which is really nice. And React shows its guts a little bit more. And even though we are Erlang heads, it's always nice to have something that's a bit more rounded, a bit more, you don't have to get too into it if you don't want to. So we continue testing until launch. We have 2 offices that we're doing this testing. We have one office in Vancouver and one office in Dublin in Ireland. And so that obviously helped. We were able to do very big soak tests, as Seán pointed out. We planned as well a MySQL Cassandra hybrid thing for one of our services, just because it was one of our really, really, really critical services. That's the progress store. We had kind of planned to, write to both and then have a percentage of reads from one and then gradually move over. It turns out it was overly complex and just had too much overhead operationally and developmentally. And so we dropped it and we just went with Cassandra. So a bit about schema. So the progress score was a perfect fit. You always know the key because it's user-based, so it's just a user's progress. And it's mostly writes. You just read when you log in, and then you just update, save as you go along. So it's like perfect, really, really simple. Like schema was just, it wrote itself. Sorry. So then we have presence, a bit more relational. It was kind of a little bit tricky because there was various ways to index into the data, and we had to figure out the best schema there. It's a high throughput service, and so we had a lot of tombstones. And as Seán was mentioning, the peaks and troughs of daily logins and logouts helped us actually iron out a couple of issues with that. So we had an issue. We had to use TTLs because it's obviously it's high throughput, and if someone logs off, or if they don't log off, or if they if they disconnect uncleanly, you need to just kill the data eventually. So we had an issue where we had two tables with the same TTL, but one was being written more often than the other. And so what happened was eventually one just like died or just went away. And so we had all these errors where, one thing was indexing into the other. And so we learned a lesson from it, but that was, just an interesting issue we encountered there. And then for the messaging service, it was time series data, so well suited. It's literally just, you got some messages, read the messages. But again, we had an issue with tombstones where our Nagios check actually caused it, interestingly enough. So the Nagios check was using the same partition key every time for its check. And it built up a load of tombstones in one partition. And eventually, or gradually, the performance of the cluster went down, and it eventually hit a point we couldn't sustain. So we were like, what is going on? We figured it out. It was all the tombstones in the one partition. And we actually it was actually a Cassandra bug, which actually had been fixed already, but we had not deployed. So yeah, that was an interesting issue we encountered. So lessons we learned from schema: keep it simple. So the shift in thinking of coming from a MySQL background or an SQL background, it's not a relational DB. You need to rethink the way you model your data. Listen to Patrick. He knows what he's talking about. We worked with him on it and figured it out. It was really, really good. So keep it simple. Get your partition keys and your clustering keys right, and Cassandra will just do what it does best, which is be really fast and distributed. Do not ignore the CAP theorem. You should live by it with Cassandra. Cassandra is very tunable, and you can tune the consistency up if you want, multiple nodes to come back and give you your data and make sure they're the same before it returns. You're going to have latency issue, or you're going to have higher latency because of that. So you need to make the trade-offs and just make sure that you're doing what's right for your application. And load test with real numbers. Some issues are not evident in unit tests, and they will not show their faces until you do them at scale, or you do them, as we said, with peaks and troughs and whatever else. That's it. Hand over to Seán.
So config. The default settings when you install Cassandra, at least this is back for DSE 314, 316, probably not what you want. They're somewhere in between a VM and a high-performance server, and they don't really work for. They didn't work for either very well for us, at least. We took a quick run through the config, changed a ton of settings based on common sense, and then reverted a few of them. After we kind of did our quick run through the config with the kind of the common sense settings, we then did a kind of a change one setting, load test for 3 to 4 hours, check results, compare it to the previous load test, and then load test again. We never touched the heap. If we had more time, we possibly would have looked at it, especially after seeing some other talks and here and other YouTube videos we looked at. It does look possibly a worthwhile thing to do, but again, it takes a fair bit of time, I would imagine. There is an appendix at the end of the talk where we list all the config changes we made. So when the slides are distributed, I'm sure you can see that. So the hardware we ended up going with. We ended up going with two Intel. So some background to this. In Demonware, we typically have 2 specs of hardware each year. We have kind of an app spec, which is high CPU, high memory, and pretty crappy disks, and then DB spec, which is low CPU, lower memory, and very good disk. So for the Cassandra, we ended up merging the two pretty much. We went with 2 Intel CPUs at 2 gigahertz. We went RAID 1 with 2 40 gig SSDs, 32 gigs of memory, and 1 gig non-dedicated network. So I suppose some of the explanation to this. Talking to Patrick and DataStax, they were really pushing the RAID 0 thing. And it got us to thinking about the cap theorem a bit more, and it got us thinking about kind of relational databases and traditional databases versus something like Apache with their high availability, where typically you don't care if nodes die. We're not really used to that, so there was kind of internal discussion as well as discussion with DataStax. And it ended up being a case of we trust our hardware pretty good. Our hardware vendor is very stable. We get very low failure rates in hardware, and disk failure rates is probably the highest we get, and even they're pretty low. So we decided RAID 1 would suit us better because we'd actually have to replace hardware less, it'd be less effort, and better for the game. Disk capacity was our bottleneck, so we ended up pretty much having to scale the cluster up based on the disk size. Now, that's kind of why you've got a high CPU there, because the plan is we can increase our disk size when required. We can go up to 1 terabyte or maybe 2 terabyte when they come out. And when we do that, we don't touch CPU or memory or anything else. They'll be fine. So monitoring. When we first started doing our load tests, we ended up not only load testing Cassandra, but Graphite as well. One of the settings in the Graphite reporter was how often to send metrics. So we didn't really notice or see this too quickly, and it was sending metrics at 1 a second. So we had a 60-node cluster for load testing, and we were sending from each node about 170 metrics every second. So that kind of half brought down Graphite. So we quickly changed that to our normal, which is kind of 1-minute metrics. The key cache hit rate is an interesting metric we used a lot, and we thought we were doing very well until we understood it better. So on the key cache hit, we were typically seeing us about low 90%, low to mid 90%. And we thought, this is great. We're doing good. And then one of the other operations engineers after lunch looked into it a bit and noticed we're actually only about 60 or 70%. What was happening is when compaction was happening, compaction would read all the SS tables, that would bump our key cache hit to 100%. So on the average, which is the number you generally see, you see 100%. So to get the actual key cache hit, you have to go for the column family key cache hit versus the actual queries done, and you can get the accurate one. That didn't bite us, but it could have been bad if we were relying on it heavily. Nagios, the next thing. So we generally use Nagios for our monitoring. And typically, a new service comes along, you Google Nagios service name, you get a lot of plugins. Didn't work so well with Cassandra. There was very few plugins available. We ended up doing a lot of it ourselves. And Jalokia helped a lot with this, where Jalokia will export the JMX metrics and JMX in general over HTTP. And then you can quite easily write your own checks or your own tools to actually change JMX settings. I'll use HTTP interface, which is, again, we're a Python Erlang shop, so getting into Java and Java tooling and JMX wasn't something anyone really wanted to do. So the fact we could easily do it over HTTP was really good. We're still changing what we're actually monitoring and alert on. We've gone through several iterations of doing long and short-term read latency, write latency checks. And the problem is when you deploy a cluster, it changes over time. So if you look at a metric, so during load testing, for instance, one metric may not have gone over half a millisecond. So we said, right, we alert at 2 milliseconds, because that's giving you fair buffer time. You don't want to alert knock, and you don't alert people kind of just on the case something going up without actually something critical happening. But the problem is when you do repairs, possibly, or your cluster kind of starts seeding in more, that may change. So you're constantly kind of tweaking the metric, tweaking what you're actually alerting on and monitoring. So some gotchas we hit. vNodes and rec awareness. Again, this is specific to 3.14/3.16 for DSC, which is approximately Cassandra Apache 1.2 point some late version. We had problems with vNodes and rec awareness, where enabling rec awareness when using vNodes led to about a 30% data distribution difference on some nodes. And as I mentioned, our main capacity issue was actually disk capacity. So when we started seeing some of our nodes have 30% more than other nodes, that was pretty bad for us, so we decided to turn rec awareness off. We weren't really using rec awareness, we actually had a blade system. So what we were trying to do was use a kind of a chassis awareness based on rec awareness, but eventually didn't end up going with it. Load balancers weren't really a gotcha, but because we were using the old Python driver, we were doing SQL over Thrift. So we're using the old Python driver with no awareness of node awareness or token awareness. So we put load balancer in front of it all. During, I think, halfway through our load testing, we realized we must get the clients to reconnect every 10 minutes. Because otherwise, in a production situation, if you need to expand your cluster, and you're not actually reconnecting every 10 minutes, you're just leaving a persistent connection open, then you're not actually going to use any new node you add to your cluster. So we had to reconnect in for every application server spec for every 10 minutes. And then our dev cluster differs from production, or did. Dev for us is production as well, because game studios actually develop against dev. So dev is prod, the certification environment, that's also prod, and prod is also prod. So we have very little testing environments. But in our development environment, we typically use VMs. So we built out Cassandra on VMs, and it was pretty much after our load testing. It was about 6 months after kind of the whole project started. And we ended up having problems within a few weeks, because we used the same config as our production, which we kind of load tested, and we tested for months. And of course, the same config didn't work very well. Stuff like our throttling was turned off for compaction, memory size for the heap, a lot of this sort of stuff we had to modify. It hit us pretty hard, and eventually we actually did push for getting dev to be the same as production, at least for Cassandra, because I think we ended up wasting about a week or two debugging issues which weren't affecting the game, but were affecting this development environment, which was kind of important. We also ran a couple of issues before launch around the network. So during the evaluation period, where we had testing with 2 different DCs, we hit a problem with the network capacity. Not network capacity as such, but each individual connection was only pushing up to about 1 or 2 megabytes. But the overall link was 2 gigs, I think. We spent about a month debugging into that, and eventually it turned out it was right to the IPsec tunnel, so we ended up doing a GRE tunnel. But we thought it was fine, because when we got to production, it's 2 different DCs, so it's never going to hit us again. So we went to production, and sure enough, hit us again. So we ended up doing the same thing. After another month of testing, we ended up doing the same thing again, GRE tunnel and not turning off IPsec. We tested each individual component of the network and each area, and it all worked fine, except when you do the full link, and then it all failed horribly. So, launch was boring, thankfully, as Patrick mentioned in his talk. In the first week, the dev manager came over to my desk and asked to simulate, second week, came over to my desk and asked to simulate a node failure. Because, we put the practice in, we got documentation, we did run books, we've gone through it all, but you never really know what it's going to be like until you actually do it in prod. So let's, take a node down. So I was quite pleased to tell him a node did die in the first week, and no user experience was affected, it all worked as expected. We 2 of the nodes died over Christmas. This didn't go as well. The nodes designing themselves were fine. That didn't cause any problem with the cluster. And what did cause a problem was repairing the nodes. So replacing the nodes and then running repairs, that caused a lot of compaction. Then the repair would actually stall in cases. You have to kill the new node and then put the node in again and then start repair again and hope the repair would work this time. So it didn't affect users too badly. I think the latency went up by about 10 or 20 times, but we had a kind of pretty good buffer there, so that wasn't a problem for us. But it did cause NIGA alerts to spam and knock to start ringing us every 10 minutes or so. And explain to other titles. So this talk was again about launching Call of Duty with Cassandra. And now that it worked well, and we've actually seen that it works well, reduces operations time, we're actually planning now to use other titles with it. We've put a certain aspect of Diablo onto it, the newest Diablo, Reaper of Souls onto it. And we're hoping now for next year to put more titles onto it.